Good morning, everybody. If we can start with some green check marks, please. We'll get started here in a second. Normally, Tuesday mornings, we've been having that little foods PE, but obviously you guys are here. And for those of us who aren't here, that's on Thursday this week. So Mrs. Wood will be talking about some of the electives on Thursday morning. She tries to wrap up that stuff. Today, we are going to finish up Unit 7. I've received a few Unit 7 learning guides, but I want to go through anything you guys might have had in terms of questions on Unit 7. And then we will jump into Unit 8. Unit 8 and 9, there's only, I think between the two of them, there's only 5 sections. So this stuff's going to go fast. We'll likely finish it up by the end of next week, which gives us about a week for review, a week and a half. It's actually probably closer to, well, no, it's a week and a half. Week and a half for review for the final. And I'm still trying to decide what the final is going to look like, so don't ask me yet because I don't know. But I'll try to have a better idea of what that's going to look like for Thursday this week. So I'll give you guys plenty of time. And that's about it for now. Does anybody have specific questions about anything Unit 7? So we could be talking things from the learning guide, things from, there's those extra practice sheets. I know we kind of finished up last day with questions. You guys had some fission fusion type questions. We looked at some of the extra practice type deal from these fission fusion guys here. Anything there at all? I'd be happy to go through Unit 7 stuff. If not, we'll just continue on with Unit 8. Yeah. Costin, do we have more than a yeah? So Unit 7, the big ideas we had were alpha, beta, gamma decay with the equations that look really similar to these behind me. And then we had half-life. And then we had fission and fusion. So those are the 3 big concepts from Unit 7. I'd be happy to go through anything there. Learning guide, anything related to Unit 7. If not, I'm just going to continue on with the course into Unit 8, which we might even, well, we're not going to finish it today. We'll definitely finish Unit 8 next day. All right, Costin, if you have a question on the learning guide, throw the number in the chat, section number, page number, and we can go through it. Anything on here, anything at all. I feel like I've done a lot of the learning guide thus far. Page 7, 5, and 6. So I did 5 already. There's 5. And number 6 asks, what's the difference between radioactive decay and the reaction scientists can force? What do we think? Natural radioactive decay and the reaction scientists can force. I'm assuming that in the actual course, there's something that refers to this question. I could come up with a lot of different answers, but I'm thinking something for number 6 in terms of, trying to think of a specific example of something that we can find some differences in, but I can't really think of anything on my toes here. Difference between natural radioactive decay and the reaction scientists can force. I'm going to go that they're mainly similar, but I'm sure there's some little finicky thing that's different about them. I'm just going to go similar for now. Did anyone find in the course where it describes what the difference is? So maybe like natural decay is going to be things like alpha, beta, and gamma, whereas reactions that are forced are going to be things like uranium 235 plus a neutron. So maybe natural is going to be sort of smaller, and we can force, we're good at forcing big things. If I were to just guess, I would say that the reactions we're going to force are going to be larger atoms because they're easier to, they're more unstable and easier to break apart, whereas the natural radioactive decay is going to be smaller atoms because they would be harder to induce to break down. And beyond that, I'm not sure what I was looking for. I could go look it up and find it out, but I don't have that kind of time. So there's 5 and 6 done-ish on 6, but done. And then number 11. Fusion is actually much more efficient at creating energy than fission. Why is humanity not using fusion reactors instead of fission reactors? So all of the nuclear reactors we have on Earth, well, not all of them, the majority of them are fission reactors where they take some large particles like uranium, plutonium, break them down, harvest the energy from that. But if you could stick hydrogens together, it's more efficient, more energy is released. Why are we not good at fusion yet? We're getting there. We're getting really close to being able to fuse things together. The big reason is fusion reactors need very high temperatures. And right now, when we have a fusion reactor, they're the most common ones are in the shape of kind of like a donut, like a three-dimensional donut. And they get plasma, which is a state of matter like solid, liquid, gas, but very high temperature. The plasma whips around the inside, and it's enclosed in really large magnetic fields, so the plasma doesn't actually touch the sides, because if it touched the side, it would just melt through whatever was there. So that's the largest sort of hurdle against fusion reactors, is that the temperatures have to be so high, and we're not really good at containing the plasma yet. We're getting there though. Doesn't that help a little bit? Perhaps. All right. Anything else from the Unit 7 learning guide? Things that you didn't understand, questions about, things that you'd like to go through? All right. I'm going to hope that you guys will get the Unit 7 learning guide in probably today. Oh, there's another one. Thanks, Jonah. Page 13, page 8. I think that's the one just down below here. We talked about that one last day, 2 days ago maybe. Elements heavier than iron cannot be formed in stars. They're instead formed when stars explode. When stars blow up, it's called a supernova. I was actually doing some reading the other day, and I found that we can make heavier elements actually, there's kind of 3 ways. The supernova is kind of the most common one. The second way is when you get 2 neutron stars collide. They actually make really heavy elements. So I didn't know that. Now I do. And there you go. Neutron stars form when stars, kind of like our sun, run out of gas, literally run out of hydrogen, and they kind of compress on themselves. and space is big, but neutron stars are heavy, so gravity pulls them together, and boom, they smash into each other. We get some heavy elements as a result. Most stars are bigger than our sun. Page 2, number 9, for sure. Determine the number of protons, neutrons, electrons for each symbol given below. So this is getting back to the idea of isotopes, where we have atoms of the same element. So it could be phosphorus, iron, or uranium here in the examples. And they have different numbers of neutrons. And typically, once you get away from like the typical number of neutrons an atom has, they become unstable and become radioactive and want to break down to become more stable. Does that help you a little bit, Jonah? Perfect. No worries. Anything else? Going once, going twice. Sold. All right, we're going to move on to what we will call the physics unit. Technically, Unit 7 was physics, but it kind of looks like chemistry. Unit 8 is vectors and displacement. And basically, this is called kinematics. It's the study of motion. And in grade 10, we start at fairly basic level talking about how objects move, and it kind of leads into grade 11 physics if you decide to take that. So we want to be able to describe motion, and the reason we want to be able to describe motion is so we can predict where things are going to be. So when you start in grade 10, you talk about objects moving in straight paths, forwards, backwards, or up and down. And then in grade 11, you start talking about objects moving in multiple dimensions at the same time. So like projectiles being launched. I can tell you where an object will be after a given amount of time, or we can predict where an object will land based on how fast you shot it from whatever you launched it. And so this is kind of what it's leading into. But for now, we start at a very basic level. So just as a general question, what words do we use to describe motion? What sort of words can we use? And then to maybe stir your thoughts a little bit, if I told you I lived 13 kilometers from the school, would you know where I lived? I actually do live 13 kilometers from the school. When I ride my bike, I track it. 13 kilometers. So 13K from the school. Where do I live? Anybody know? Why or why not? Somewhere's downtown. Well, this school's downtown, so 13 kilometers from downtown, could be downtown somewhere. But would you know where my house was if I told you I lived 13 kilometers from the school? Could you find it? No. Why couldn't you find my house if I told you I lived 13 kilometers from the school? What sort of problems are we running into here? Thank you, Eric. So there's no direction. If you know the school is in the middle of a circle and the radius of the circle is 13 kilometers, my house would be somewhere on that circle 13 kilometers away from the school, but you wouldn't be able to figure out exactly where it was because I haven't indicated a direction. And this is why when we talk about all of the things we do talk about over the next week and a half, it's extremely important to include a direction with your measurements, and that will make it very clear as to what you're actually talking about. So direction makes a big difference, and we use fancy words, but you guys will know them already essentially. So quantities that are measured or counted have a magnitude, but also may contain a direction. So we use the word magnitude to refer to the size of a quantity. So we could be talking about a distance like 13 kilometers. That would be the magnitude. And then if I said 13 kilometers south, well, then you'd know where I went to get home, 13 kilometers south. And we call these things vectors. If you have a magnitude and a direction together, those create what we call a vector. And it's just a number. If I said I'm traveling 13 kilometers per hour, well, the magnitude is 13 kilometers per hour. The direction could be north, south, east, west, up, down, left, right. When I put those together, I get a vector. If I'm just talking about, traveling at 50 kilometers per hour, that's what we call a scalar. So these are the two different physics words that are really important, vectors and scalars. Vectors are things with a direction. Scalars don't have direction. So if I said I live 13 kilometers from the school, that's a scalar. You don't know what direction it is. If I said I live 13 kilometers south of the school, well, now you know where I live, and that is a vector. So there are lots of things that don't have direction associated with them. A big one is time. We can't say, it doesn't make sense to say 25 seconds west, unless you're talking about an object moving, and then you're talking about a direction. So the kind of the vocabulary words that you'll hear a lot are vectors and scalars. Vectors are anything with a magnitude and direction. So you could have speed. Speed is a scalar. You give it a direction and it becomes a vector. And it comes with velocity. So these are all the words that are kind of associated with this unit. So scalars, magnitude, vectors, magnitude, and direction. So we're going to add the two vectors below. What would the resultant be? So the best way to represent vectors is by using arrows. And arrows are really great because they can have different lengths depending on how much of a quantity you want to represent, and they include a direction. You put a little arrowhead on one end, I can tell which way this is going. Now when we talk about direction, we don't necessarily mean north, south, east, west. We can mean up, down, left, right. As long as we have some sort of indication of where this thing is going, we consider that to be a direction. So if I added the two vectors here, I have a little arrow that has 25 meters and then another arrow that is 10 meters, and they happen to be going in the same direction. They're both going to the right. What would be the resultant vector? So if we had to add these two things together, what would be the resultant? So in a very basic level, we can do this. So I have my first arrow, I forget what color it was. That's 25 meters. And then I have a second arrow, hoping for red. There's my second arrow. It's going to be 10 meters. So when I draw these vectors, I'm going to add them together. Now this is kind of a trivial example. They're pretty straightforward. But when I add these things, I want to go from the start. So here's my start. And then draw an arrow that goes to where I ended. And this black arrow is called the resultant. And in this case, that arrow, the black arrow, would be 35 meters. And then we're going to have to the right. And the resultant is always going to be drawn from where you started to where you ended. Now that might not make a whole lot of sense right now because we've just drawn two arrows to the right, but sometimes we're going to have multiple arrows going in many directions and the resultant's going to look a little bit different. So let's jump back into the notes. All right, another example. Add the two vectors below, what would the resultant vector be? Where are we going to end? or what would be the resultant of these two things? So I have 100 meters per second, which is a velocity. That's how fast you're going, meters per second to the left. And then I'm adding to it 30 meters per second to the right. I wonder if I have this in OneNote. I do. It's amazing. All right, I've already done it. Should have erased it. Didn't. I think it was Joshua who was all over it. All right, so here we go. I'm going to have some starting point right here. Here's my starting point. And from my starting point, I'm going to draw this blue arrow, which is 100 meters per second. So that arrow is 100 units long. And then I am going to start from tip of that arrow. I'm going to start the tail of my next arrow. I can actually draw this up a little bit higher. So tip to tail, I'm going to go back 30 meters per second because this arrow was going 30 meters per second the other way. So my resultant will be from where I started to where I ended. And in this case, this is 70 meters per second to the left. All right. So those are kind of two arrow examples. I think we have some additional examples that have multiple arrows. Get this stuff out of the way. All right, so there are 1, 2, 3, 4, 5, 6 examples here. And I'd like you to attempt to add these vectors together. Essentially, you're just adding arrows. The numbers are all fairly straightforward. And we'll just see if we can add them together. So for letter A, I'm going to have some starting point. I'm going to have one arrow going to the right, has a magnitude of 5, and then I'm going to have a second arrow, which is going to the right with a magnitude of 5, and my resultant will be from where I started to where I ended. So in this case, 10 to the right. All right, the second one, again, I'm going to have some starting point. My first arrow is going to the right, has a magnitude of 5. My second arrow is going to the left, has a magnitude of 5. So where can I draw an arrow for the second one? What is my resultant going to be? If I go to the right 5 and then I go to the left 5, have I left where I started? Not really. I'm right back where I started. So I'm at 0 meters away from where I started. I guess it's not necessarily meters. I don't know what the units are. It's just 0 units. All right, see if you can try C, D, E, and F is just the same thing except it's going up and down instead of going left and right. Take a little break, give you a couple seconds to try to sort that out, and I'll meet you back in like a minute or two. All right, guys. Hopefully you had a chance to try those last few. The important thing about drawing these vectors or these arrows is that the number is loosely, tied to the actual length of the arrow you're drawing. So, if you see an arrow that's 5 and then you have another arrow that's 15, the second arrow should be 3 times longer than the first arrow. So, did anybody have any questions on, oh, it looks like I lost one of my black arrows here, on C, D, E, or F? Or are we experts on vectors? Now, in this example, we're just drawing, arrows, and these numbers don't have anything really associated with them. But eventually, we're going to start talking about things like distances and speeds. And when we compare the vectors, they'll have sort of more meaning to them. Are they negative numbers? Negative's a funny thing in physics leads. So we'll talk about in just a second here that negative sign just indicates direction. So if you look at some of the examples you see here, you see a number like -5 or -10 or -15. Anything that's negative is going to the left. And numbers that are positive are going to the right. So we use negatives in physics to represent things that are going in a different direction. So we typically will assume anything going to the right, anything going forward, anything going to the east, all being positive, and anything that's going to the left, down. Yeah, same thing as a number line, exactly. That's a way better example than what I was rambling on about, but anything to the left, anything down, anything to the west, generally will be negative. So give you a bit of an idea of the difference between positives and negatives. All right. So we've added vectors in kind of, left, right, or up and down. But what happens when our arrows go in different directions? What if I said I walked 5 meters to the right and then walked 10 meters forward or something like that? If I have sort of 2 dimensions, what sort of things happen when I run into these types of scenarios? The process is exactly the same. We'll just end up having to use Pythagorean theorem to solve these guys. No, the Pythagorean theorem. Won't be that bad, promise. All right, so let's get rid of some of this stuff. Give all the answers away. We'll see if we can't just do it ourselves. All right, this is looking like not the pen I was hoping for. Letter A up here. We'll do it over on the side. So exact same process. We draw our vectors tip to tail. So we start with our 5. So our 5 was going that way. That's 5. And then we have another vector. I will start it tip to tail. And this one has a length of 10. So I guess unlike a number line leads, we can deal with things in multiple dimensions. Now our resultant is that black line. It's going to go from where I started, the beginning of the blue arrow, to the end of the green arrow. And in this example, we end up with a right angle, and we can use the Pythagorean theorem to solve for the length of this arrow. So a squared plus b squared is c squared. The order of these shouldn't matter. 5 squared plus 10 squared equals c squared. 5 squared is 25. 100 squared or 10 squared getting ahead of myself, is 100 c squared. Adding those together is going to be 125 c squared. And in order to get just c, take the square root of both sides. I wonder if I have a calculator here somewhere. I think I might be able to just grab it. Maybe. There it is. All right, so I'm trying to take the square root of 125. Do I have a square root button on this calculator? I do. Square root 125 is 11.18. We'll just call it 11.2. So 11.2 is equal to c. All right, the second example is really similar to the first one. Instead of going across 5 and then going right 10, I'm going up 10 and then right 5. Now, are we thinking really hard about this? What is the answer to this question going to be without doing any work? Any guesses as to what the answer to this might be? No guesses? 11.2. Eric, how did you guess that? That's right. That's amazing. Random guess. Perfect. Well, I'm going to take the random guess you've made, and I'm going to say that this this picture would just fit right onto this side of the same question up above. So it's the exact same answer because it's the same shape. Instead of going right and then up, I've just gone up and then right. So it's essentially the other half of what would make a rectangle. The next one, we'll call it C. C is starting here, I'm going up 10, and then I'm going left another 10. And my resultant is going to be from where I started to where I end. And in this case, I'm going to use the Pythagorean theorem again. A squared plus b squared is c squared. And 10 squared plus 10 squared is going to be 200. I guess I can write that in. And then I will take the square root of 200. I don't know what the square root of 200 is off the top of my head, but my calculator does. And that is going to be 14.14. We'll just call it 14.1. I want that to be black. Makes more sense. So 14.1 is equal to C. All right, the last one's a tricky one. Letter D. Normally I've just had 2 arrows. Now I'm going to have 3 arrows. And I'm going to do it the exact same way though. So here goes. I'm going to start right here. And my first arrow is going to go down 5. And then I'm going to go to the right 5. And then I'm going to go up 10. There's 5. There's another 5. That's 10. So I'm going to start from where I started, and I'm going to go to where I ended. And I need to somehow make a right triangle out of this. Now, I know the bottom of this has a length of 5, and I know this right side has a length of 5 because the whole thing's 10 and half of it is 5. So to figure out what this is, I'm going to have to go 5 squared plus 5 squared, c squared, and the square root of 50. I don't know what that is. My calculator does. So I'm going to go square root of 50 is 7.07. We'll call it 7.1. Is the length of that last one. Is this in the learning guide? I'm not sure, Costin, is it in the learning guide? I'm going to assume that because you can't find it, it's maybe not in there. Let's have a little peek. Vectors and displacement, we haven't talked about that. We've got some distance. We're talking about vectors. Oh, number 8 looks like we've done it already. And that's about it thus far. So some of it is in the learning guide, Costin. Just got to look for it a little bit. The notes should match up fairly well at this point, I believe. So distance. We're going to talk about distance and we're going to talk about position. And they kind of sound like the same thing, but they're a little bit different. So distance is a scalar quantity. Just describes how far you are away from something essentially, or the difference, distance between 2 points. And it's kind of like the first example I used, a person ran 400 meters. We don't know what direction, but they ran 400 meters. Position is a vector quantity. So remember, scalars don't have a direction, vectors do. If we say position's a vector quantity, we know exactly where the object is. So the school is 3 kilometers east of my house. And when we talk about distances and positions, we always use meters. Generally speaking, you'll see some examples with kilometers and some examples with centimeters and millimeters. Generally, things will be in meters. It doesn't really matter what you end up with in terms of units, as long as you're consistent with your units. So the little pictures down at the bottom here, if we talked about distance, so the first image, we've gone from home to the store. How far have we gone? So we started here at home, we went, drove to the store. How far have we gone? We've gone 10 kilometers. And what would be our position? Well, our position would be 10 kilometers, we've gone east of home. So we started at home and we went 10 kilometers east of home to end up at the store. Now the second picture, we've gone from our home, we drove to the store, and now we went back home again. So how far, what distance have we traveled? Well, we went the initial 10 kilometers to get from home to the store, and then we went back 10 kilometers. So how far have we gone? Well, we've gone 20 kilometers. But what's our position? So our position is where we started. So we've actually, our position is 0 meters, but our distance, or 0 kilometers, sorry, but our distance is 20 kilometers because we went to the store and then back. So position is different than distance. Distance is how far you've traveled. Position is how far are you from where you started. It gets kind of confusing. So far we have distance, we have position. Now we're going to talk about displacement. Displacement is the straight line distance and direction from one point to another. Displacement is equal to the final position minus the initial position. And remember, position is how far are you from where you started. So this displacement is essentially your change in position. Just going to skip that for a second. Let's look at an example. A car drives 3 kilometers north, then 2 kilometers west, then 3 kilometers south, then 2 kilometers east. What is the car's total distance traveled and its displacement? So what we're doing now is we're taking all these little arrow pictures that we've drawn so far, and we're going to try to make sense of kind of a word problem. So just reading it, I'm driving 3 north, and then 2 west, and then 3 south, and 2 east. Trying to form that in my head to figure out where I am. It's going to be really confusing. So this is why you should always draw a picture. We're going to do these 2 examples. All right. So far we have done just arrows, but now these arrows are going to represent how far we've actually gone. So let's see if we can't just figure things out here. I'm going to start here, and I'm going to go 3 kilometers north. Maybe I'll draw a little compass here, north, east, south, west, just to kind of remind myself what direction's which. So I'm going to start here. I'm going to drive 3 kilometers north. So there's 3. And then I'm going to drive 2 kilometers west. 2. I guess I should write in some numbers here. And then I'm going to go 3 kilometers south. And then I'm going to go 2 kilometers east. Run out of colors. That's 2. So there's 2 questions here. What is the distance traveled, and what is the displacement? All right. Why does it do that to me? All right, the distance. Remember the sort of definition of distance is how far you traveled. So what was the distance? How far did we go in this example? We did indeed go 10 kilometers. So that was 3 plus 2 plus 3 plus 2 is going to give us that 10 kilometers. And then the displacement is a little bit different. The displacement's how far am I from where I started. So I start and end at the exact same spot, this spot here. So Josh is exactly right. At 0 kilometers is my displacement. I am exactly where I started. I am starting and finishing at the exact same spot. So I have technically my displacement, my change in position, how far I am from where I started, is 0. But the distance I traveled was 10 kilometers. I went north, and then west, and then south, and then east. So I did this big square. I traveled 10 kilometers. But how far am I from where I started? I'm 0 kilometers from where I started. So that's an example using kilometers. Let's do another example using meters. All right, so we're always going to draw a picture. A child walks 3 meters north, so let's start our child off here, and the child is going to walk 3 meters north, and then the child walks 7 meters south. It's 3, so there's the initial 3, and then we go down another 4, so there's 7. Another 2.5 meters south. And then and then 5 meters north. Okay, so I'm going to draw in my resultant from my initial starting point to where I finished. So again, I'll ask the same 2 questions. What is the distance traveled? And what is the displacement? We've got 17.5 for distance, so we're going to add all of these things up, and hopefully that works out to 17.5. So I have 3 plus 7 plus 2.5 plus 5. That is indeed 17.5. And we're going to include meters. And then the displacement. This is a little bit trickier. How am I going to figure out what the displacement is? How far am I from where I started? .5 meters. And Leeds is important, not just Leeds, but everyone, to include direction with that. So in this case, you're 1.5 meters south. Is 1.5 the right answer? Let's see if we can figure that out exactly. If I were to draw a little line across here, that would be 3. This green would be 4. So I went down 4, and then down another 2.5. So I've gone south 6.5. And then I've gone north another 5. So it looks like this black arrow is going to have a length of 1.5 meters. I like it. So again, if I go up 3 and then I go down 3, and then from here down to the bottom is going to be 6.5. I go up 5. What's left? 1.5. Little deduction. Made a big mess of all that. All right, so that's how we can put this stuff into practice. All right, what else do we have here? So Leeds, you asked this question a little bit earlier about the negative signs, and we're just going to make it clear. When using vector quantities, opposite directions are given opposite signs. So if I say something's forward, generally that's positive. If it's backwards, it's going to be negative. So remember, displacement is how far you are away from where you started. So between 0 seconds and 15 seconds. Let's try to figure out what's going on with this little person. And you'll see a few diagrams like this where they give you positions in different times. And we need to just kind of figure out what's going on. So above the person's head, you see 0 seconds. So this is the starting point right here at 0. And then it looks like t is 5. So 5 seconds later, this person walked to here. And then another 5 seconds have passed. The person's kind of walked back to here. And then another 5 seconds pass, and the person has walked to there at 20 seconds. Oh, sorry. I skipped 15. So 10. And then all the way over to here, and then the person walked back there for their 20-second mark. So that's kind of what's going on here. It's a little bit confusing to just stare at it, but if you kind of try to wrap your head around it, you can figure it out. So the question's specifically asking between 0 seconds and 15 seconds. So we're looking between 0 and 15 seconds, and we're trying to figure out the person's displacement. So Josh says 15 meters. Does anybody disagree or agree with Josh? And one thing that I will challenge you, Josh, and all of you, is that when you're talking about vectors, you need to include a direction. So what does the direction look like in this particular question? Left. I like it. We could also, if you look along this axis here, on our little number line, things are measuring east to the right and west to the left. So I would like 15 meters left or 15 meters west. Those will both work. How do you know it's 15 though? Because if I look here, Josh, I see that at 15 seconds, he's actually 10 meters left. So where did you get the 15 from? Why is it 15 instead of 10? I see it at time 0, where I started here, t equals 0. I'm already 5 meters away from here. So when we talk about displacement, it's our final position minus our initial position. Or how far have you gone from where you started? In this particular example, if you're starting there, there's 5 meters, there's another 5 meters, there's another 5 meters. So that's 5, there's 5, there's 5. The displacement is going to be 15 meters to the left or 15 meters west. And when we include our cardinal directions, we'll always put them in some square brackets. So this would be worth just jotting down somewhere on your learning guide. These are what we call common sign conventions. Anything that's to the west or left is negative. Anything to the right or east is positive. Anything north or up is going to be positive, and anything south or down is going to be negative. So we try to stick with this sign conventions to not confuse ourselves or our nice teacher, Mr. Borden. So north, up, positive, down, south, negative, west, left, negative, east, right, positive. Just makes everything a little bit more straightforward if everyone plays by the same rules. All right. Distance displacement again. A car starts at a point 30 kilometers north of town. Draw a picture. After traveling to a point 40 kilometers straight south of town, what is their total displacement? This is a town. It's a beautiful picture of a town. The car starts 30 kilometers north. And this distance is 30 kilometers from town to where I started. After traveling to a point 40 kilometers straight south of town, so the car goes and ends here, and this is 40 kilometers south of town. What is the total displacement? So we purposely make these questions, I don't want to say tricky, but we try to make you think about the actual definition of displacement. So displacement is the distance from where you started to where you end. So Josh, although you are, I guess you're not right. Eric's going to go 60 kilometers or 70 kilometers south. If the question had been asked differently, Josh, if I said, how far are you away from town, or what's your position relative to town, you would be right. But because the question asked for displacement, and this is why we kind of really, try to make it very clear the differences in the definitions of these words. Displacement's from where you started to where you ended. So 40 kilometers south of town would be your position relative to town. That's right. But how far did you go from where you started to where you ended? In this case, you started up here and you ended all the way down there, and that's 70 kilometers. So the displacement is 70 kilometers south. So again, it's just kind of semantics, trying to get the sort of the definitions of these words down. Because different questions, I could have written everything out the exact same way, and I could have said, what is the person's position? And then Josh, you would have been right with 40 kilometers south of town, but it asked for the displacement. And the displacement's how far have you gone from where you started to where you ended, or the resultant. Let's see if we can get another one. A child walks 3 meters in a positive direction. Pardon me. All right, so positive direction. What does it mean by positive direction, and does it matter? Could we do this diagram so positive direction's up? Would it make a difference if we did a question where we said, okay, positive is up, or if I said positive is something to the right? Would the question be any different? Would our answer be different? No. So it doesn't matter. You can pick whatever direction you want being positive, as long as you're consistent. So generally speaking, right, east, positive, up north, positive. If you just immediately see the question, you think, okay, I'm going to go everything positives up, then do the question this way. If you think everything positives to the right, that's just kind of what pops into your head, then do the question that way. And it won't make a difference at all to the answer. So just because there's more room going to the right, I'm going to go ahead and go to the right. So a child walks 3 meters in a positive direction. The child then turns around and walks 7 meters in the opposite direction. Label that. 3 meters. is 3. 1, 2, 3, 4. That's 7 meters. If their final displacement is 0, what was their last walk? So again, we're coming back to this word displacement. And displacement is how far you are away from where you started. So in this example, it's saying their displacement is 0. They are exactly where they started. They're ending where they began. So it's asking how far was their last little section of walk. So if I wanted to get back to where I started, and again, this is the start. If I want to get back there, how far did I have to go? Well, I'm going to go with 4 meters, but I need to include a direction. So in this case, I've walked to the right, and everything to the right is positive. So 4 meters in a positive direction. To get back to where I started. Let's see what else we have here. It's about time we take a break, I think. Maybe I'll leave you with a few questions to work on. All right, so common sign conventions, we did that. We did these 2 examples. All right, so we have 3 questions here. I'll leave these with you. We'll take a little break. There isn't a lot to go through, so what I'll do is I'll give you guys maybe a 10-minute break, and then we'll come back and we'll go over these 3 examples. And then I think there's one other slide. And then once we've done that, we'll have a little peek at the learning guide and see if we can iron out a few things there, and then I'll just leave you for the day. So we'll just take a 10-minute break, grab a drink, snack, take a walk, and try these 3 questions, and we'll come back and we'll sort them out. Thank you. Good luck. Hi guys, welcome back. Hopefully you got a chance to get up, the blood moving a little bit, and had an opportunity to look at these three examples. So again, it comes kind of down to the meaning of the words. So we have distance is how far you've traveled, position is how far you are away from something, and displacement is how far are you away from where you started. So in example number 3 here, what is the total displacement of the boy between 0 seconds and 15 seconds? That's not helpful. All right, so 0 seconds, the boy is where? Looks like 0 seconds is right here, and then 15 seconds is over here. I think that's the exact same question we just did, is it not? Yeah, it's the same as this one. 15 meters left. Same deal, or 15 meters east. So starting from here and going this way, we have 15 meters, we said west or left. Either one would be fine. Example number 4, in the graphic above, what is the boy's displacement between 15 seconds and 20 seconds? So, same question. Between 15 seconds, so starting here, and then ending at 20 seconds. So how far have we gone from where we started to where we ended? That looks like 10 meters to the east, or to the right. The last one was total displacement of the ball, of a ball that you drop off a 50-meter cliff. So we'll just draw a quick little picture. Here's a cliff, and our cliff is 50 meters high. We drop a ball, and it goes and hits the ground. The displacement is the distance between where you started and where you ended. So I'm going to say that that ball traveled 50 meters. What sort of direction am I going to give this? I have to include a magnitude, 50 meters, and I want to include a direction. So what sort of direction could I give this ball that fell off a cliff? I could call it south. Is there something else I could give it instead of south? I could say down as well. And Eric, you're right, I could just call it negative 50 meters. And the negative is implying down or south. So that would be good. That would be good. And that would be good. Essentially, there's 3 different ways to answer this question. They're all equivalent and they're all correct. As long as you're clear as to what that is, you should be fine. But the direction is important. So down, south, or negative 50 meters are all important. All right, so these types of questions don't come up a whole lot, but sometimes we need to do a little bit of Pythagorean theorem to sort things out. So we should be able to use the Pythagorean theorem. So let's just practice that a little bit, and then we'll have a look at the learning guide. So a boat travels 30 nautical miles east, and then 20 miles south, and then 5 miles west. What is the boat's total distance traveled and the displacement? So this black arrow is the displacement, and the distance has no direction associated with distance. So the distance is just how far you went. So let's start with the distance, because that's going to be the easiest to calculate. We're going to start with a 30, then we're going to add to it, I suppose I should write in some units here, 30 miles. And then we're going to add to that 20 miles. And then we're going to add to that 5 miles. And together those will give us our distance, which is equal to 30 plus 20 plus 5 is going to be 55 miles. All right, so that was the easy one. The tricky one now is the displacement. How far are we from where we started? All right, so we need to kind of make a right angle triangle out of this thing. So I know the side's 20 from the picture, but how far is it from here to here? It's not 30, because 30 is the whole thing. What's left for just that little section there? Yeah, if I went 30 all the way across, and what's left is just going to be 25. So if I break out my Pythagorean theorem, I'm going to go 25 squared plus 20 squared c squared. I don't know what 25 squared is. 25 times 25. Yeah, I don't know what that is. But my calculator does. 625. So 625 plus 400 is 1,025. C squared, take the square root of both sides. Square root of 1,025 is 32. So C is 32 miles. So I am 32 miles from where I started. What do you think for a direction on this one? You know, if I had a compass right here, I said this is north, this is south, this is east and west. How could I represent, you know, this sort of direction on a compass? What could I call that? Southeast? I like that. So I've gone kind of southeast. So 32 miles southeast. Sort of the general direction I'm traveling there. So that'll work. That's clear. I've got a magnitude, 32 miles. I've got a direction that's southeast. Looks good. A fish swims 40 meters north and 10 meters east and 40 meters west. Find the resulting displacement. So similar type of question. I'm going to start with 40 north. And then I have 10 east. And then I have 40 meters west. And I'm asked to find the displacement, how far I am away from where I started. Again, I need to kind of make a right angle triangle out of this. And if your drawing gets kind of messy, you can just redraw it, just right next to it. There's no shame in that. If it makes more sense to do that. I know this is going to be 40. And this will be, I went 40 and then 10, so this is going to be 30, according to my little diagram there. All right, so 30 squared plus 40 squared, c squared. Uh, 4 times 4 is 16, 3 times 3 is 9, 900, 1600, added those together, should be 2500, is that right? I think so. And square root of 2500, what number times itself is going to give me 2500? I'm thinking that is going to be 550. 50, 50, is that right? Is C? Yeah, I think it's 50. And we had some units here, so our displacement is going to be 50. The units were meters. And again, I need to come up with a direction. My arrow's kind of going this way. So I'm thinking that that is going to be, we'll call it northwest. Perfect. I like leads, thank you. So I have a magnitude, 50, direction northwest. One last one, a plane. A plane. All right, so a plane flies 300 kilometers. The numbers get bigger, but nothing changes. So instead of this being 3, it's 300. 300 north, 200 west. That's it. Just north and then west? Seems so easy. What is the plane's total distance traveled and the displacement? So draw on my displacement arrow where I started to where I ended. Let's start with our distance. Distance doesn't have a direction associated with it. It is just how far you went. So if I went 200, I mixed those up, I suppose. I should have probably written the 300 first, but I went 300, then 200. My distance is going to be 500. My displacement, on the other hand, it's a little trickier. I'm going to have to use the Pythagorean theorem, so I'm going to go 200 squared plus 300 squared, c squared. 200 times 200 is 40,000, I believe, and 90,000. 4, 9 is 13, 130,000. And then I'm going to take the square root. And I don't know what the square root of 130,000 is. Did I get the other ones right? 400 squared. Double check. I was off by a 0 or 2 there. Oh, sorry, it was 200 squared, not 400 squared. 40,000 plus 300 squared, which was 90,000, 130,000. Take the square root of that. It's going to be about 360.5. We'll call it 360.6 kilometers is C. And again, our direction is going to be the same as the one we just did. So the displacement is going to be 360.6 kilometers northwest. All right, so a little bit of math. Kind of looks more like a math class than a science class maybe. The really, really important things for this section are it sounds silly, but it's the vocab. The difference between position, distance, displacement. These are three different things. Position, how far you are away from something. Distance is just how far you went. And displacement is how far are you from where you started. So the questions, I could set up the questions completely the same. For instance, number 3 here, and then just ask you for the distance traveled. And then you would look at it and be like, okay, what's distance? You got to remember what the distance is. Or I could have the exact same question, ask for displacement. Or I could have this exact same question, ask the position. And sometimes they might even be the same, some of the answers. So just try to get straight in your head what is what. Let's take a peek at the learning guide here, and then we will call her a day. So for number 4 here, it's kind of an important question. The difference between scalars and vectors is that scalars are things that have number but don't have a direction. Vectors are things that have a direction. So if I look in the table above it, anytime I see a direction, so north, I've highlighted here, I've got downstream, that's a direction, down, and southwest. Anytime I have something with a direction associated with it, it is a vector. And then if I have something without a direction associated with it, like 1 kilogram, or I can have time. These are all examples of scalars, no directions associated. So that's an important concept. What else do we have? Can 3 parallel vectors in unequal magnitude add to 0? So I did that. Can 3 vectors of different magnitudes and directions add to 0? Show a diagram. We did number 8 in the notes. We didn't talk about number 7, but we will next day. I'll just tell you what it is now, just so you can have it in your learning guide for now. So that should say change. That didn't really look like change. So we'll talk about these guys next day more. So delta T and delta D. Delta is this triangle symbol. It's actually a Greek letter in their alphabet. It looks like a triangle. It is a triangle, but they call it delta. And we'll talk more about that next day. What else do we have here? You guys should be able to add those. You should be able to do these 9, 10, and 11, hopefully. 12, 13 are non-right angle ones. You should be able to do those just like what we just did. And then velocity is where we're going to pick up next day. We'll start talking about velocity. So there you go. I guess the most important thing is you guys focus on finishing up Unit 7. Some of you guys have finished it already, so you are laughing and ready to move on to this Unit 8 stuff. For those of you who have yet to finish Unit 7, you should get that done as soon as possible. If you want to come in for help on it or anything for that matter, usually Wednesday afternoons we have available for that sort of thing, so you can just send me a message and I'll make sure I'm here tomorrow afternoon from usually sometime between 1 and 3. And that's about it for now. It's super duper important that we just finish as strong as possible. So we have 3-4 weeks left, and there's really like a hard deadline at the end of it all. So far at the end of term 1, or I guess term 3, if you weren't quite done all the materials, like no worries, finish it up and you'll get it done before the end of the course. It's all good. But when we get to the end of the course, I can't extend the deadline into summer vacation because nobody's here to mark any of the stuff. So this hard deadline is, it's coming, and you don't want to be rushing to do a bunch of stuff at the last minute. So if you can focus just really hard on just one section at a time, just kind of getting them out of the way, get the test written, get the work in, get those learning guides marked, things like that, you should be doing fine, and that'll give you lots of time to review for the final exam. So I'm going to do my best. I'm trying to think, I have a meeting today and tomorrow. I'll do my best to get that final exam set up so everyone's clear on what that's going to look like. I can't guarantee you'll have it done for Thursday, but I can try my darndest to get it done for next Tuesday for sure. So you guys will know exactly what the final exam is going to look like. Make it easy. I'm not actually going to make the questions, Jonah. I'm just going to steal them off old provincial exams. And the only thing that I am just kind of working on in my brain right now is find easy questions. Okay. Which sections we're going to focus on. And I mentioned, because we wrote that midterm exam, which really focused on sections in the biology unit 1, 2, and 3. There's just a little bit of unit 4 stuff in there. We'll probably, there's unit 10 in there before as well. So we'll probably focus on unit 4, 5, 6, 7, and 8. So chemistry and the last 2 physics units. It is the harder material in the course, and when I say final exam, I don't want you to think like, oh no, it's just like the be-all end-all of everything. And no, the final exam is just going to be like another midterm exam, and it'll be worth the same as the first midterm you guys wrote, which you guys all did fairly well on. So nothing to be overly stressed out about, but I mean, you do want to take it seriously and be as prepared as possible. So I'm going to decide what that's going to look like for next Tuesday for sure. I might have it done for Thursday, but I'll give you kind of a breakdown of how many questions are on each chapter and what to expect in terms of that stuff. So does anybody have any questions before we sign off for the day? In terms of Unit 7, anything from Unit 8, anything about the course, general? Well, while I'm here, I never know if Mrs. Ward talks to you guys about this stuff, so I'll just pretend like she didn't. I think this Friday is, that's this Friday, yeah, right there, Bear Creek hike. So 11 o'clock till 12 at Bear Creek Provincial Park on the west side. We just do a hike of the loop up to the waterfall and back down. It's a nice little walk outside, so that's this week. Next week, that's not next week. There we go. Next week we do a little walk downtown on Friday and then come back to McWilliams. Usually we have some ice cream. It's a good one to come to. And then the following week, now I have a big mess here. It's not the following week. There it is. Essentially Friday, June 16th will be the last day to submit any work. So that's kind of the hard deadline for everything to be in by then. And then that leaves a couple days on the following week. I can find it. There it was. A couple days on the following week for kind of review. And then we have our final exam on Wednesday the 21st. It says 9 to 11:30. We're going to try to make it from 9 till 11. You get an extra 30 minutes there if you need it. And then you're done. That's it. And I have these 2 classes on the 19th and 20th down as review if necessary. So basically we won't probably do anything from the studio on those days. I'll just be in my office. I'll give you guys some practice exams to go through and some review booklets and things like that. And if you have questions about them, you can just sign into Blackboard and ask. At that point, you know, all the material's been taught. There's going to be nothing that's new. So it's kind of up to you guys to review and prepare for the exam. So those last 2 classes on the 19th and 20th is just for your benefit. I'll make myself available. You can either come into the building or just online in Blackboard, ask questions, anything you're confused about. But I don't think they'll be like regularly scheduled classes unless you guys want a regularly scheduled class, and then we can do that. But it's kind of up to you at that point. So that's what the next few weeks have in store. I know it seems crazy, but we're almost done. This Unit 8 only has 1 more section. I think Unit 9 has 3 sections, so we'll definitely be done Unit 8 by the beginning of next week, and then Unit 9 will fly by real quick as well. And the rest of Unit 8 and 9 both kind of look like today. It's a little bit of math, a couple definitions, And there you go. I didn't see anybody have any questions while I kind of rambled on there, so I will leave you with that. If you want to come in for some help on stuff, tomorrow will be a great day. If not, hopefully we'll see you on Friday for the Bear Creek hike, and see you in class on Thursday. We'll finish up Unit 8 and maybe even start Unit 9. Probably not. We'll finish up Unit 8 next day. So have that. You might want to print off Unit 9 as well, just in case. So there you go. Thank you very much, everyone, and I will see you on Thursday. Bye-bye.